If you want to bake a cake, you might buy a dozen eggs. But if you want to make a single molecule of water, you need exactly 2 hydrogen atoms for every 1 oxygen atom. Chemists use their own grouping word to manage these ratios on a massive scale. It is called a mole, and instead of 12, it represents a quantity known as Avogadro's number. That number is 6.022 times 10 to the 23rd, or roughly 602 hexillion. It is so large that even if you could count 10 million atoms every second, it would still take you billions of years to finish a single mole. This presents a massive practical hurdle in the lab. Chemical reactions require us to combine a specific number of particles, yet those particles are far too small to see, let alone count by hand. The mole solves this by acting as a translator. It creates a bridge between the invisible mathematics of atoms and the tangible measurements we can actually use in the real world. For solids and liquids, scientists historically solved the counting problem by using weight as a proxy for quantity. This starts with molecular weight, the mass of one isolated molecule measured in atomic mass units, or AMU. Molar mass is that same value scaled up to 1 full mole. For an entire mole of carbon-12, those 12 atomic mass units become exactly 12 grams. In the lab, this means if you need a mole of carbon, you don't need to count atoms, you just weigh out 12 grams. In chemistry, weighing a substance is mathematically identical to counting its atoms. Chemists use a central conversion equation, N equals m divided by m. The little m is the sample mass in grams, read directly off the scale. The big M is the molar mass, found on the periodic table. Dividing them gives N, the total moles. This formula allows us to execute precise chemical reactions without ever needing to interact with a single individual atom. Weighing works for solids, but gases are a different story.
They are incredibly difficult to capture and weigh accurately on a traditional scale. In 1811, Amedeo Avogadro proposed a radical idea to explain how these gases behave. He claimed that equal volumes of different gases contain the exact same number of particles, regardless of the gas. This means volume tells you the quantity in moles, even if the particles in one gas are much heavier than the other. However, gases are sensitive. If you add heat, the molecules move faster and push further apart, which increases the volume. Because of this expansion, scientists lock the temperature and the pressure. Only then can gas volume reliably reveal the particle count. For decades, the official standard for the mole was tied to a physical weight, the number of atoms in exactly 0.012 kilograms of carbon-12. But that definition relied on the international prototype of the kilogram, a physical metal cylinder kept in a vault. If the mass of that cylinder fluctuated even slightly over time, the definition of a mole would shift with it. To solve this, the scientific community met in May 2019 and decided to decouple our measurement standards from physical objects. Today, the mole is defined by an exact, fixed mathematical value for Avogadro's constant. It no longer depends on the weight of a piece of metal or a sample of carbon. By fixing the mole to a specific number, scientists removed the uncertainty of a physical reference. We now have a global standard, linking the behavior of individual particles to the materials we build and measure every day.